What if I told you that there exists a mirror image of everything we know, a twin universe made of antimatter? Imagine a world where every particle has a mirror image, an antiparticle with the same mass but opposite charge. This isn't the plot of a science fiction novel, but a mind-bending reality in the realm of particle physics. This is the Enigma of Antimatter. The concept of antimatter was born out of the theoretical equations of physicists, a fascinating idea that took form in the mathematical language of quantum mechanics. It suggests that for every particle in our universe, there exists a counterpart, an antiparticle. Like a reflection in a mirror, it's identical in every way, save for one crucial aspect: its charge. Where an electron carries a negative charge, its antiparticle, the positron, carries a positive one. It's this opposite charge that defines an antiparticle and sets antimatter apart from the ordinary matter we interact with every day. But here's where things get truly perplexing. Theoretical models, grounded in our understanding of the Big Bang, suggest that the birth of our universe should have produced equal amounts of matter and antimatter. Yet when we look around us and out into the cosmos, we see a universe teeming with matter and a conspicuous absence of antimatter. This has led to one of the greatest mysteries in physics. Where has all the antimatter gone? This question has puzzled scientists for decades, sparking numerous experiments and driving research into the properties and behavior of antimatter. Why does our observable universe appear to be almost entirely matter-based? Why isn't there an equal amount of antimatter? These are questions that continue to baffle physicists and cosmologists alike. The intriguing absence of antimatter in our universe has become one of the greatest mysteries in the world of physics. As we delve deeper into this enigma, we are not only exploring the fundamental nature of our universe, but also challenging our understanding of the very fabric of reality. When matter and antimatter meet, they annihilate each other, releasing energy in a process that's both fascinating and explosive. This is the basis of the annihilation process, a dance of destruction where particles and their antiparticle twins collide. Picture this: an electron, a tiny particle of matter, meets its antimatter counterpart, a positron. They don't shake hands. Instead, they obliterate each other, converting their mass into pure energy in accordance with Einstein's famous equation, E equals mc squared. This annihilation process is incredibly efficient. In fact, it's the most efficient energy conversion process known to science. To put it into perspective, if we could convert just a gram of antimatter into energy, it would be equivalent to the energy output of a nuclear bomb. But don't get too excited just yet. Harnessing this energy is not as simple as it sounds. Antimatter is rare, incredibly rare. The particles we need for this process are not just lying around for us to scoop up. In fact, to produce just a single gram of antimatter, we'd need to run the Large Hadron Collider at full power for several billion years. And even if we could produce antimatter on a large scale, containing it is another challenge altogether. You see, antimatter has a tendency to annihilate with matter on contact, and since our world is made up of matter, well, you can see the problem. Creating a container that can hold antimatter without allowing it to come into contact with matter is a task that would give even the most seasoned scientist a headache. So while we can dream of a future where antimatter powers our cities and spaceships, for now, it remains just that, a dream. Theoretical predictions and sci-fi imaginations aside, the practical application of antimatter for energy production is a puzzle that we have yet to solve. While the energy potential of antimatter is vast, harnessing it remains a monumental challenge. The discovery of antiparticles, such as the positron, marked a significant breakthrough in antimatter research. This statement might sound a tad complex, but let's break it down. Antiparticles are simply the mirror images of particles. They carry opposite charges compared to their matter counterparts. The positron, for instance, is the antiparticle of the electron. While the electron carries a negative charge, the positron carries a positive one. The discovery of the positron back in the early 20th century was a turning point in the world of particle physics. It was the first hint that our universe might not be as matter-dominated as we initially thought. But the positron story doesn't stop at just being an antiparticle. It has a far more compelling role. It is a star performer in a medical imaging technique known as positron emission tomography, or PET for short. Now, PET scans are fascinating. They help doctors see how our bodies are functioning at a cellular level, providing critical insights into conditions like cancer, heart disease, and neurological disorders. How does it work? Well, it's all about the positrons, A small amount of radioactive material that emits positrons is introduced into the body. As these positrons encounter electrons in the body, they annihilate each other, releasing energy in the form of gamma rays. These gamma rays are then detected and used to create detailed images of the body's internal functions. It's like having a superpower, being able to see into the human body without any surgical procedures. So, the discovery of the positron, this tiny antiparticle, has had a remarkable impact on medical science. It has enabled us to peer into the human body in ways we could never have imagined. It's a perfect example of how understanding the fundamental forces of the universe can lead to practical applications that benefit us in our everyday lives. Antimatter, it seems, has found its way into practical applications, helping us see the human body like never before. Despite our advancements, antimatter continues to be a subject of speculation, intrigue, and relentless pursuit. This elusive mirror image of matter, with its antiparticles bearing opposite charges to their matter counterparts, holds profound implications for our understanding of the universe. Theoretical predictions suggest that the Big Bang produced equal amounts of matter and antimatter, yet our observable cosmos is dominated by matter. This discrepancy, known as the baryon asymmetry problem, has become one of the most perplexing puzzles in the realm of particle physics. The quest to solve this mystery has led scientists to scour the cosmos for traces of antimatter. They're searching for antimatter galaxies, cosmic rays containing antimatter particles, and other potential signs of this elusive substance. Aided by advanced telescopes and particle detectors, researchers are exploring the farthest reaches of the universe with a hopeful eye on unmasking antimatter's secrets. In this quest, leading particle physics laboratories, such as CERN, play a pivotal role. At CERN, the world's largest particle physics laboratory, scientists are generating and studying antimatter under controlled conditions. They're using cutting-edge technologies to contain antimatter, a task as challenging as capturing a shadow due to antimatter's tendency to annihilate upon contact with matter. Through these meticulous experiments, researchers hope to unravel why antimatter is so scarce and whether it behaves differently than matter under the same conditions. But the quest for antimatter is not just a scientific endeavor. It's a journey into the heart of the universe, a pursuit of knowledge that could reshape our perception of reality. If we can unlock the secrets of antimatter, we might also gain insights into the fundamental forces that govern the cosmos, potentially revolutionizing our understanding of how the universe works. The search for antimatter is not just about understanding the universe, but potentially revolutionizing our comprehension of the fundamental forces that shape it. So, what have we learned about this elusive twin of matter? Antimatter, a mirror reflection of the regular matter that makes up our world, is a fascinating concept in particle physics. Comprising antiparticles, which hold opposite charges to their conventional counterparts, antimatter prompts profound questions about the fundamental nature of the universe. Theoretical predictions suggest an equal creation of matter and antimatter during the Big Bang, yet the observable universe is predominantly matter-filled, a puzzle that has intrigued and baffled scientists for decades. We've delved into the annihilation process, where particles and antiparticles collide, resulting in an energy release that is both efficient and explosive. Though this process has fired the imaginations of science fiction writers, in reality, the practical application of antimatter for energy purposes remains a monumental challenge. This is due to antimatter's scarcity and the difficulty of containing it, a challenge that researchers at leading particle physics laboratories, such as CERN, continue to tackle. We also journeyed through some of the significant breakthroughs in antimatter research, notably the discovery of antiparticles like the positron, the electron's antiparticle. This discovery has had a profound impact on advancements in medical imaging techniques like positron emission tomography, showing us that the applications of antimatter extend beyond theoretical physics. We've also touched on the ongoing quest for antimatter in the cosmos, a search that continues to fuel our desire to understand the universe's complexities. The delicate balance between matter and antimatter is a central element in the cosmic drama shaping our universe, driving scientists in their endeavor to unravel its mysteries and revolutionize our understanding of the fundamental forces at work. As we continue to unravel the mysteries of antimatter, we edge closer to understanding the cosmic drama that shapes the universe. Until next time, stay curious and keep exploring.